Great. Okay. Good morning. So yesterday we were talking about some of these what are called gas laws. And so the first one was Boyle's law, which says that the pressure of a gas times its volume, P1 V1, is equal to, it's constant, so it's equal to the final pressure times the final volume. And this was done at constant temperature, T for temperature, okay? And then we had the second relationship, which was Charles's law, which said that the volume of a gas divided by its temperature is constant. So you can write that as a proportionality, a ratio. The initial volume divided by the initial temperature is equal to the final volume times the final temperature, and this was at constant pressure. And then we had Avogadro's law, which said that essentially the volume of a gas is constant, or I should say the molar volume of a gas is constant. So if you take the volume of a gas and divide it by the number of moles, that's got to be constant. That's called the molar volume. So again, this is at constant P. It's actually at constant temperature and at constant pressure, okay? So those are three relationships. And the third one, Avogadro's law, you can even use that in a balanced equation. So yesterday when we looked at the example, we saw how you could take the volume of one gas divided by the coefficient and set that equal to the volume of another gas in the equation divided by the coefficient in that equation of that gas. And the reason that works is because the idea, or I should say, these gas laws suggest that it doesn't matter what gas you have, the volume of a gas just depends on the temperature, pressure, and number of moles. It doesn't matter whether it's oxygen or nitrogen. So we don't need to worry about the molar mass or anything like that, okay? Now notice that you have these constants, right? So certain things are constant. So the question, the next step is, what if these things aren't constant? What if the temperature is not constant? What if the pressure is not constant? What do we do then? And so what we do is we take these three equations and we combine them. There's a couple of different ways to combine them. The first way is through what's called the combined gas law. The combined gas law is very simple. What it says is pressure times volume is constant at constant temperature. Volume divided by temperature is constant at constant pressure. Let's put them together. And so really what you're doing is you're taking those first two and putting them together, and you get P1 times V1 over T1 is constant. So that's P2 V2 over T2. That's called the combined gas law. It's a very, very nice little equation. And what it does is it allows us, if we have all the numbers, if we have 5 out of those 6 values, right? There's 3 on either side. If we have 5 out of the 6 values, we can find the 6th one from the 5 that are given. So with this one, we don't have to worry about whether it's at constant pressure, or constant temperature, or constant volume. All of them can be changing. That's perfectly fine. We've got the equation to deal with that, okay? I do want to point out that when we're dealing with temperature, remember that the temperature is in Kelvin. So we talked about that a little bit yesterday. So any equation that has temperature, make sure you have it in Kelvin. And of course, the relationship there is that the temperature in Kelvin is equal to the Celsius temperature plus 273.15, okay? Typically, they give you the temperature in Celsius, and you have to figure out the Kelvin. So that's one way. That's one way to deal with it. Another way is what's called the ideal gas law. So this is a second equation that you'll see. And what it says is typically written this way. The pressure times the volume, so sort of like Boyle's law, is equal to N, the number of moles of the gas, times R, which is a constant, we'll talk about that, times T, which is the temperature. Again, temperature needs to be in Kelvin. Okay, so notice that that equation also has pressure and volume and temperature, but it has the added benefit of also having the number of moles in there. The one thing that may not be familiar here is it's got this R constant. This is called the universal gas constant. And there are different values for the universal gas constant. So I'll talk about that a little bit separately when we get into it. But these are two equations that we can use, and they're actually related to each other, that we can use to discuss or to consider what happens when we have three things changing, okay? So let's take a look at an example. Okay. And so this is using the ideal gas law. So people use different terms. It's the ideal gas law is what people typically call it, but you'll see sometimes it's written as the ideal equation of state. Now that's a more technically correct name for it, but really what they mean by that is the ideal gas law. Okay, an equation of state is a relationship that describes what state a substance is in. So what its pressure, what its volume, and what its temperature is. Okay, so let's take a look at this example here. In this one, they say, oops, sorry, I'm having a little, okay. So in this one, they say that you have a reaction. They don't tell you anything about the reaction. Well, actually, I shouldn't say that. They tell you something about the reaction, but not much. They say the reaction is at 110 degrees C. So I'm sorry, 11.0 degrees C. I didn't see that decimal point. And it evolves 283 millimole of carbon monoxide gas. So then what it does is says the following: calculate the volume of the gas collected. Assume the pressure is 1 atm. Okay, and then they tell you the number of sig figs to report it to. Okay, so you're going to use this. The reaction's at 11.0 degrees C. Okay, it evolves 283 millimoles of carbon monoxide gas. Calculate the volume. Assume the pressure is 1 atmosphere. So often we run reactions that produce gases, but they're producing gases, open to the environment. And if they're open to the environment, the pressure of the gas is going to be the same as the pressure of the air. And the pressure of the air is 1 atmosphere. Okay, so let's take a look. What they gave us was the temperature. So I'm going to just start writing down numbers and labeling them. The temperature is 11.0 degrees C. Okay, so that's the first piece of information we have. The next piece of information we have is the number of millimoles of carbon monoxide gas. So the symbol for moles is N. So we'll call this 283 millimole. Okay, you can label that it's carbon monoxide if you want to. We don't need it, but that's fine. And then they tell us that we can assume the pressure is constant at 1 atm. And that's right here. And then they ask us to calculate the volume. Okay, all right. Well, we have several choices, right? There's all these equations that we've learned. Let me just list them over here. We had P1 V1 equals P2 V2. We had V1 over T1 equals V2 over T2. We have V1 over N1 equals V2 over N2. We had P1 V1 over T1 equals P2 V2 over T2. That's the combined gas law, right? And see what we got. Boyle's, Charles, Avogadro, which I noticed just thinking about it, those are the first three letters of the alphabet. But then we've also got this one, P equals nRT. So notice that two of the equations have moles in them, right? So the ideal gas law has moles in it, and so does Avogadro's. But Avogadro's law talks about two different volumes, right? It says the volume is changing. It's related to the number of moles. So we don't have two different types of moles. We only have one. We have one temperature and we have one pressure. So from that, we would say, hey, let's go for this one right here, right? That's the one that has temperature, moles, and pressure, and then you ask for volume, okay? So we'll use the ideal gas law. So how do we get what we need out of this? Well, we're looking for volume. So if you're going to use the ideal gas law or the equation of state, and you want the volume, you divide both sides by pressure. If you divide PV divided by P, that will give you V. So you'll have nRT over P. Okay, so there's your ideal gas law. Now, the only thing that we have to take into consideration are units, but also the value of R. As I said, the R is a discussion. So let's talk a little bit about R. R, you can call it, you just call it gas constant if you want to. And there are different values of R depending on the units. It just depends on the units. So let me give you a few of them. I'm going to give you, I guess I'll give you four. So the first one is the most common one. And then this is atmospheres times liters, or liters times atmospheres, per Kelvin times mole. It has 4 units in it. Okay, so that's one possible value. Another value is 8.314, I think it's 3144. And then that would be joules per Kelvin mole. It could be 0.0083144 kilojoules. We're just converting it to kilojoules per kmol. Okay, so those are 3 different values. So what you really want to do is the one you're going to pick is based on what units you have for the data. So if you look at your temperature is not in Kelvin, but all the values of R are in Kelvin. So you know you're going to have to convert that to Kelvin. Look at the units of pressure. This is the key here. Look at the units of pressure. 1 atm. Only one of those values of R has atm in it. It's this one right here. So that's the one you want to use. Just look for your pressure unit. If your pressure is in atmospheres, use that value. If your pressure is given in the units of joules or kilojoules, then you're going to use these ones. Okay. So we got our value of R. So now it's just a matter of going ahead and calculating it. So let me save it here. So we got V is equal to nRT over P. Now, we have millimoles in here, so they're not fooling around in this question. They want to give you different units so that you can do your little conversions. So we want to convert millis. So one way to do this is you could remember that there's 1,000 millis, like 1,000 milliliters per liter, or 1,000 milligrams per gram. But the other way is just to use your definition of milli. Milli is 10 to the minus 3. So this is just 283 times 10 to the minus 3 moles, right? This is milli right there, so 10 to the minus 3. And that's fine. There, that's in a little awkward notation, but it would work. The value of R we're going to use is 0.08257. atmosphere liters. Remember, we said to use this one because it had because the pressure was given in atmospheres. So our temperature is 11.0 degrees C. So let's add that to 273.15, and you get 284.15 Kelvin. Okay. And then our pressure is 1 atm. Now they only report it as 1 sig fig, but they tell you to give the answer in 3. The reason for that is they're saying it's exactly 1 atmosphere, which is, you know, just they're being, I would say they're being a little bit lazy there. They should say it's exactly 1 atmosphere, because the significance of that is that if you're trying to do sig figs, you might think that you only have 1 sig fig in your answer. But what they're doing is they're really saying, assume it's exactly 1 atmosphere. So that means that these values here become the important ones in terms of sig figs. So we got the moles, we got the temperature in Kelvin, we got the pressure, we got the value of R. So let's go ahead and put it in. I'm going to put the units in there. So 283 times 10 to the minus 3 moles. So there's your N. And I'm going to put the R in. Atmosphere liters per K mole. A lot of units for R. I think that's one reason people often like joules per K mole. It's got one fewer unit. And then 284.15. And then you divide that by the pressure, 1 atmosphere. Now I went ahead and put all the units in there just so you can sort of see what happens. You've got moles in the numerator here and moles in the denominator there. You've got atmospheres in the numerator here and atmospheres in the numerator there. You've got Kelvin in the numerator here, but you've got Kelvin in the denominator there. So you're just left with liters. So your volume is going to be in liters. Okay, so let me see if I can find a little calculator here. So 0.283 times 0.082057 times 284.15. And it looks like you get about 6. That doesn't seem right. Oh, no, that's about right. Yep. I'm sorry. Three sig figs would be 6.60. Okay. So a couple things to look at when you're doing these problems with the ideal gas law or the equation of state is make sure that you've got your moles and moles, not millimoles or micromoles or kilomoles. Make sure you pick the right value of R. If they give you the pressure in atmospheres, use the atmosphere liters per K mole. Make sure your temperature is in Kelvin, and then you're set. You pretty much have it there. Now, I actually, when I did the calculation initially, I didn't think the answer was right, and then I had to stop and think about it. And here's what I did mentally. What I did was I said, I remembered something, which is that if you take PV equals nRT, and you put in 1 mole of a gas, so you put in N equals 1, and you put in 1 atmosphere, okay? And you put in a temperature of, 273 Kelvin, which is 0 degrees C, rounded to 3 sig figs, okay? I'm just sort of estimating here. The volume would be nRT over P. And what you get is 1 for moles, 0.082057 for R, 273 for T, and then you get 1 for P, right? Right, 1 atmosphere. This particular problem that they gave us was at 1 atmosphere. Now, what I did was I essentially said, look, I remember that if you do this calculation, you get 22.4 liters. That's your answer. It's kind of a classic problem where we take 1 mole of a gas and you put it at a pressure of 1 atmosphere and you put it at a temperature of 0 degrees C, 273 Kelvin. That gives you 22.4 liters. That's a number that people remember. So what I did was I said, well, wait a minute, let's see. This is pretty close to 273. It's not that far off. And so if I had 1 mole, I would have a little more than 22.4 liters, right? Because this is a little more than 273. But I would have somewhere around 22 to 23 liters. So then I said, well, wait a minute. What's this here? 6 to 7 liters. Does that seem right? Well, if we didn't have 1 mole, we had, this is 0.283 moles, right? 283 times 10 to the minus 3 is 0.283. So that's, that's not far off from a quarter of a mole, right? 0.25 would be a quarter of a mole. So if this is 22 liters, a quarter of that would be around 6. And so my answer was 6. So that can be kind of useful for checking your answers with the ideal gas law, which is, we call it the molar volume. The molar volume of a gas is 22.4 liters per mole, meaning for every 1 mole, it's going to have a volume of 22.4 liters, okay? Now, that technically is only good at 273, right? So we're off a little bit, so we can't use that number to do the actual calculation, but we can use it to estimate it. So they often refer to that as STP, standard temperature and pressure. Which is, the pressure is 1 atm and the temperature is 0 degrees C, which is 273.15 Kelvin. If they tell you it's at STP and they tell you, or if they say it's 1 atmosphere and 273, then what you can do is you can say, yeah, the volume is equal to, the volume divided by the number of moles is 22.4. And so you just take the number of moles and multiply it by 22.4, and that'll give you the volume, okay? So that's the ideal gas law. All right. Or equation of state. They call it the equation of state, which is fine. That's a more technically correct name for it. Okay, so the next step is interconverting molar mass and density of a gas. Okay, so let's take a look at that issue. So when we look at a gas, remember what I said, I think it was last week, talking about gases, is that if you look at solids, the atoms are really close to each other, right? And they're rigid, they don't move around. If you look at a liquid, they're also really close to each other. They can move around though, right? They flow. They take the shape of the container. But they're still really close to each other. That's why we call them condensed matter. Like condensed milk, right? Condensed milk is where they take the water out and make all the ingredients that are in milk condensed. But then you also have gases, right? And so gases are different, right? Gases, the molecules are really far apart. So what happens is not condensed matter, is they have much lower densities, right? The density is how much mass something has divided by the space that it occupies, which is the volume, right? So if you look at this, we've got mass and we've got volume. Well, the ideal gas law also has volume in it. In fact, all of our gas laws have it. But in particular, nRT over P, sorry. But in particular, the ideal gas law has volume in it. So what we can do is we can say the following, that we have this relationship between matter that we talked about back in chapter 3, which we called the molar mass, right? Now, often we remember how to calculate it. We go periodic table, we add up the masses, you got your molar mass. But coming back to what the molar mass actually means is, it's the mass of something divided by the number of moles. So if I say, look, I have 1 mole of oxygen, it would weigh 32 grams. It's the mass divided by the number of moles. So if I had 2 moles, it would weigh 64 grams. So let me write this as mass M divided by moles N. And let me write this over here as mass M divided by V, or volume V. So notice we've got 3 equations here that have some similarities, that have some commonalities, right? There's density is mass over volume, there's volume is moles times RT over P, and then there's molar mass, which is mass over moles. So let me write them next to each other and show you what ends up happening if we just do some simple substitution. And for molar mass, I'm going to use the following symbol. I'm going to use a cursive uppercase M. Looks something like that. Okay, so molar mass is a cursive. Okay, there's no, I don't particularly like that symbol, but I haven't seen any symbols that are better. Sometimes people will use double M like that, molar mass like that. Fine. Okay. So what we do is we essentially just substitute. We combine these 3 together, just like we did with the ideal gas law. We combine those 3 gas laws to get that. And so when you do this, what you get is you get that the molar mass of a gas is equal to the density of the gas times R times T divided by the pressure of the gas. And that's pretty useful because what it does is it says if you can measure the density of a gas, measure the temperature, measure the pressure, you can figure out what the molar mass of the gas is, and you can actually use that to identify the gas, right? So if I found out the molar mass was 32 grams per mole using this equation right here, then I would know that's O2 because O2 weighs 32 grams per mole. If I got 44 grams per mole, I would know it's CO2 because carbon dioxide weighs 44 grams per mole. So this equation right here is a nice equation for figuring out the molar mass and actually the identity of a particular gas based on its density. So the key here is you essentially just have to measure the density, but measuring the density of something is really easy. You just take the mass, you measure the mass, and then you measure the space, the volume. So you measure the mass and the volume, you got its density. Use a thermometer, you got your temperature. Use a barometer or a manometer or some sort of other type of device, you got the pressure. And now you know the molar mass and you can identify the gas. Okay, so there's your equation right there. Of course, if you want to, you can also go the other way. If you know the gas and you know what its molar mass is, you can also find its density. So sometimes we do that calculation. A little bit less common, but let's take a look. Okay, so this is called interconverting molar mass and the density of an ideal gas. Okay, so they tell you got some unknown compound. Okay, so we don't know what it is. So that means we can't figure out the molar mass just by saying, oh, it's CO2, it's 44, right? Can't add up the atomic masses. It's just some gas. It's vaporized at 160 degrees C, meaning that it boils at 160 degrees C. So that's its temperature, right? And then we say it has a volume of 1630 milliliters at 1 atmosphere. Now, in this particular one, they actually give you the number of sig figs. They say it's 3 sig figs for the pressure, and it weighs 2.32 grams. Okay, so you know its mass, and assume it's, you know, obeying the ideal gas law, calculate the molar mass. Okay, it's pretty straightforward. So let me show you how you would go about that. You want to find the molar mass. So if you're dealing with a problem where you're dealing with a gas and they ask you for the molar mass, you know, again, come back to those equations, right? P1 V1 equals P2 V2. That doesn't have molar mass in it. We're not going to use that one. V1 over T1 equals V2 over T2. That doesn't have molar mass in it. We're not going to use that one. V1 over N1 equals V2 over N2. Well, you know, there might be something you could figure out in terms of moles, and there is a volume in there, but again, it doesn't have molar mass in there. It doesn't have mass in it. PV equals nRT. Well, you know, I mean, it's got pressure, you're given the temperature, you got a volume. So you could figure out the number of moles out of that. That's cool, right? So that's a possibility. But, you know, and then the combined gas law, no chance, right? This doesn't have really anything involving molar mass. But take a look at this one. Molar mass equals dRT over P. You got the pressure, you got the temperature. We don't have the density, but we do have volume and mass, right? So remember, density is mass over volume. So we do have the density, in fact. Okay. Now there's an alternative way to do it, which would be to take the ideal gas law, and you do have enough to figure out what n is. So you could figure out n from that equation. And then you could say, we know the mass. So your molar mass is mass over moles. So you could actually do that, right? This one you would get from PV equals nRT, and then mass is given. So that there's two different ways to do it, and that's perfectly fine, whichever way you want to do it. What I'm going to do is I'm going to go ahead and use this equation here, calculate the density, and then get the molar mass out of it. Just be careful of the units. Remember, temperature with gases has to be in Kelvin, okay? Whenever we're dealing with any of these equations involving gas laws, we want to have the temperature be in Kelvin. We want to select the correct value of R. And the density is an issue too, because R, if we look at the unit we're going to use for R, it's going to be in liters, and our volume given here is in milliliters. So let's set it up. Let's first find the density. The density is the mass, 2.32 grams, divided by the volume, which is 1630 milliliters. Now, typically, that's a perfectly fine set of units to use for finding the density, but not really with gases. With gases, it's typically in grams per liter. If it was just liquid water, grams per milliliter is perfectly fine. But when you're dealing with gases, you want to have it in liters. So I'm just going to go ahead and put, actually, you know what I'm going to do? Instead of calculating that out, I'm just going to put the volume into liters. Okay. So remember, milli is 10 to the minus 3. So one way to do this is 1630 times 10 to the minus 3 liters. So that's one way to do it. Another way to do it, if you've seen this method, is to say, look, it's 1,000 ml per liter. Oops, sorry. We want to get liters. It's a liter per 1,000 ml. So you get 1.630 liters. 1.630 liters is the same as 1630 times 10 to the minus 3. So either way, you get the right answer. Okay. So we have our volume in liters. So let's write that out as 2.32 grams over 1630 times 10 to the minus 3 liters. So 2.32 divided by 1630 times 10 to the minus 3, and you get 1.42. Okay, oops, sorry. Let me see, hold on one second. 1.63, okay. 1.42. Three grams per liter. Okay, all right. So that seems, yeah, that's right. Okay. Let me just make sure I didn't write one of the numbers wrong. Nope, I got it right. Okay. All right. So there is our volume, and then there's our density. So you've got your density right there, 1.423 grams per liter. So now your molar mass is your density, 1.423 grams per liter, times your R. Now, again, the way you determine which value of R is really given by the pressure. If this is an atmosphere, you want to use the value of R that has that unit, and that's the 0.08, 2057 atmosphere liters per mole per kmol. And then let's do our temperature. Our temperature is 160. So that would be what? 373, 433.15. Okay, so 433.15 Kelvin. So nRT, I'm sorry, dRT over P. P is easy because they gave it 1 atmosphere. Okay, so there's your molar mass. So keep in mind when you're doing molar mass, you know, the lightest gas is hydrogen, and its molar mass is 2 grams per mole approximately, right? So if you get an answer that's less than 2, if you get 1 or half, there might be something wrong. Gases generally have limits to how heavy they can be. So if you get 1,000, that's a pretty heavy gas. There aren't many gases that weigh 1,000. So you're going to look for anywhere from 2 to maybe like 100 or 200. There are some exotic gases that weigh 300, but generally they're, you know, generally they're less than 100. Okay. So let's take a look. We got 1.423 times 0.082057 times 433.15. And it looks like you got about 50.6. And then the dimensional analysis is your liters cancel, atmospheres cancel, kelvins cancel, and you got grams per mole. Okay, so 50, that's 3 sig figs is what they asked for. It's 50.6 grams per mole. So that's all it's really asking for. It's not asking you to identify the gas. I'm not sure what weighs 50.6. It's hard to say. You'd have to go through all the different elements and add them up to make sure, because it could have 2 atoms, it could have 3 atoms, it could have 10 atoms, right? So for example, at that temperature, C7H16, that's a gas at that temperature. So, you know, there's a lot of possible different gases at that temperature, so it's hard to say. Okay, so 50.6. Okay, let me show you one more, because we can go the other way too. So in this particular question, they say calculate the density of the gas. And then they give you the name. Chlorine, I'm sorry. Chlorine, Pentafluoride. So calculate the density of chlorine pentafluoride at exactly 10 degrees C and exactly 1 atm. Okay, and then they tell you assume it's ideal gas. That obeys the ideal gas law, which is perfectly fine. Okay, so in this particular case, if we wanted to know the density, you got to know the mass and the volume. So again, there's more than one way to deal with this, but you can certainly use this one because we know the gas, we know what gas it is. So we can use this one. You can use that equation because we know what the name of the gas is, so we can figure out what the chemical formula is and find out what the molar mass is, right? We know that this thing is chlorine, Cl, penta is 5, right? So ClF5. So we can find the molar mass very easily. We're given the pressure. We now have the molar mass. We know the value of R. We're given the temperature, and you can find the density. So that's a perfectly fine way to do it. So let me rearrange the equation. We want density. So I'm going to multiply both sides by P. Right? So now you have pressure times molar mass equals dRT. Now, again, we want D, so we're going to divide both sides by RT. And there you go. So it's just a matter of putting in pressure times molar mass dividing by RT. That will give you the density. An alternative way to do it would be to figure out, well, you don't know the volume, right? So we just know the temperature and the pressure. So you could find the molar volume. And then, yeah, I think this is probably the easiest way to do it. Okay. So let's take a look. First, let's figure out what the molar mass of this is. Chlorine is 35.45 and fluorine is 19.0. Okay, so there we can calculate that molar mass right there. So 35.45 plus 5 times 19, and you get 130. Okay, so there's your molar mass. So we have our pressure, we have our R. Of course, the temperature is at 10 degrees C. We want to add to that 273.15. So you get 283.15. So there you go. And there we go. Okay, so we should be able to get it. So density is pressure, 1 atmosphere. Actually, they say exactly 1 atmosphere, so I don't need to write 1.00. So there's your pressure. Molar mass is 130. 0.45 grams per mole. And then your R values, 0.082057 atmosphere liters per k-mole. And then 283.15 Kelvin. Now, when you do these calculations, make sure you divide by both of those numbers. So it's not a bad idea to multiply everything in the top and then multiply everything in the bottom and then do the division. So 0.082057 times 283.15. So you get 23.234 down here, and then do the ratio. So 130.45 divided by 23.234, and you get 5.61. And then our units should be grams per liter, because the atmospheres are going to cancel, the moles are going to cancel, the kelvins are going to cancel, so then you get grams per liter. Okay, so just be careful. You may often recall that the density of water is 1 gram per milliliter. This is grams per liter. So we're not claiming this is more dense than water. It's per liter. So it's over a huge volume, whereas the density of water is over a small volume, right? The mass of water is over a small volume. So we would say in the units of grams per milliliter, this would be equal to 0.00561 grams per milliliter. So it's much less dense than water at room temperature and atmospheric pressure. Okay. The density of a material depends on its temperature, but it also depends on its pressure. Both of those are important. Okay. All right, so there you go. So there's essentially just 2 ways you can do that problem. One is that you figure out the density and get the molar mass. The other one is you figure out the molar mass and you get the density from that. Okay. So let me look at, I think we have enough time here to look at the section 4, which is solving for a gaseous product. Okay. So in this particular type of problem, what we're going to do is we're going to be given some material. It could be a solid, for example. So I'm just going to write A for just some material. And maybe we're going to heat it. Now, when we heat something, we often use a little triangle. It's an old symbol to mean heat. You put it above the arrow. And so when you heat this A, it might turn into, a product which is also a solid maybe, but then also it might produce another product which is a gas. And so if you see a gas, you can generally use the ideal gas law. And so we can use the ideal gas law to do certain calculations of materials in these problems, okay? So it's really just kind of doing mass mole conversions, just like we did before. The difference here is that the moles is coming from the ideal gas law. So let's take a look. So the type of example they give you here is they say, look, you got these old Roman ruins, and the Romans made many of their buildings out of bricks, which is generally heated clay, and mortar. And mortar is the stuff that holds it together. A mortar is very similar to concrete. So a key ingredient of their mortar was quicklime, which is calcium oxide, which they produced by roasting limestone. So limestone is kind of cool. Limestone is predominantly calcium carbonate, right? And it's a stone, right? Like they have quarries, you can go dig it up, and different deposits of this have different qualities and different features. Some of the really beautiful quarries of limestone are in Italy, and so the Romans were able to make these beautiful buildings using limestone. The Egyptians, they used limestone in the pyramids, not as the actual blocks, but as blocks that they put on the surface of the pyramids. And limestone is essentially white, and it reflects light really well. So in the time period that the pyramids were built, the surfaces were actually very reflective, and it's said that you could see the reflection of the sun from these buildings, I don't know, 50 miles away or 100 miles away, something like that. Over time, people stripped the limestone to use it to build other things. So in this particular problem, what do they say? They say, write the balanced equation, including the physical state symbols, for the decomposition of solid calcium carbonate into solid calcium oxide and gaseous carbon dioxide. So let me go through that. That's our first step. So we're going to write the equation. And for decomposition, right? That was back in chapter 3. Of solid calcium carbonate into solid calcium oxide. It's called lime. We call that lime, right? So calcium carbonate is called calcite, and calcium oxide is called lime, and carbon dioxide gas. Okay. Now, calcium carbonate, which is limestone, it actually comes from the oceans, essentially. So the oceans, all these shells from creatures that had shells that died, the shells settle down to the bottom. It's pretty hard to digest those shells. So over time, they get pressed down. The weight of mud and then finally rock compresses them down. And now you get these it essentially turns it into stone, right? Over millions of years, it turns it into stone. Okay, so let's take a look. Let's write the equation. So what it says is we're going to write the decomposition. Decomposition means breaking up. So we're going to take solid calcium carbonate. So calcium is Ca, right? Carbonate is one of the polyatomic ions, CO3. Now let's make sure that we got the formula right, because remember, when you write the formula for an ionic compound, metal with nonmetal, you got to have the charges balanced. So when we look up calcium, it's in the second column, group 2A. So it has charge plus 2. When we look up the carbonate ion, that's a polyatomic ion, it has a charge of minus 2. So they're balanced, right? So we don't need to have 2 calciums or 2 carbonates. Just 1 to 1 will work because they have the same charge. Okay, physical state of matter, solid. Decomposes. Now, it doesn't say that you're heating it, it just says it decomposes, but it's done by roasting, it's done by heating it. So I'll put a little delta up there. So it's going to turn into calcium oxide. So what's calcium oxide? Well, calcium, again, Ca. Oxide is oxygen, so that's O. Again, we got to check the charges, make sure the charges balance. And if they don't, then we got to change the formula to balance those charges. So calcium, second column, group 2A. Oxide, that's easy because that's in group 6A. 6A is -2. So we're set. They both have opposite charges. Solid calcium oxide, or quicklime. We also tells us to write carbon dioxide. Now here we don't worry about the charges, right? That's a molecular compound. 2 nonmetals, carbon's in group 4A, oxygen's in group 6A. If they're both nonmetals, that's molecular. And for molecular, we're not doing charges. You could do oxidation numbers, but we don't do charges because they're not ionic compounds. They're not actually comprised of ions. They're comprised of atoms, okay? So there we go. Check, see if it's balanced. It is, right? That particular decomposition is balanced, okay? So now this is where we get to the problem. So after you write this equation, they say, suppose that 86.0 liters of carbon dioxide gas, so of carbon dioxide gas, are produced by the reaction at 310 degrees C. So now we know it is being heated, right? They tell you it's 310 degrees C. So you know it's hot. Actually, it's 310.0, but that's okay. At exactly 1 atm. Okay, perfectly fine. So we got our pressure, we got our temperature, and then they tell us how many. So that's volume, right? So now the question is, calculate the mass of calcium carbonate that reacted. Okay, very simple question. This really gets to the issue of what you did back in chapter 3, which is the moles of one substance, from the moles of the other. So here's the approach for this type of problem. We're talking about a gas, CO2. All those numbers they gave you are for CO2. And you've got volume, temperature, and pressure. So if you're given information about a gas, typically you can use the ideal gas law. And notice what you are given, PVT. So there's only one variable we've not given, and that's N. So what I'm going to do is I'm going to solve for N. Divide both sides by RT, and that'll give you N. Put that in. Why am I doing this? I'll show you why we're getting this, but all that information that they give you is so that you can get N, so you can get the moles of CO2. So let me go through it. We have 1 atmosphere. That's an exact number, by the way. 86.0 liters, that's V. 0.082057. I'm not going to put the units in there because it takes up too much space. And then your temperature. Now remember, careful, gas law, you got to add 273.15. So if you add your temperature, you get 583.15. Okay. That's going to give you moles. So now you have the moles of CO2. So 1 times 86 divided by 0.082057 divided by 583.15, and you get 1.797 moles of CO2. Okay, now here's why I did that. The question is, calculate the mass of calcium carbonate. They didn't tell us anything about the calcium carbonate. They didn't give us like how much calcium carbonate was in there, anything except about CO2. So here's what we do. Remember, a balanced equation, and this one is balanced, allows you, if you know the amount that's produced here, if you know that one, you can also calculate how much of the other one was produced, right? Just by using the ratios in the balanced equation. Likewise, if you know the amount of one of the products, you can find the amount of the reactant that was reacted, okay? So you can find all of them from one. If I'd given you the mass of CaCO3, you could figure out how much CO2 is produced. You can also go backwards. So here's what we're going to do. We're going to say, look, you got 1.797 moles of CO2, and it's 1 mole of CaCO3 is reacted to form 1 mole of CO2. That's what we did back in chapter 3. So it's the same thing. So because this equation is balanced with all the coefficients being a 1, it just ends up being the same number. And there you go. You got the moles of CaCO3. Now that's not the question. The question is they're asking for the number of grams, the mass, right? Calculate the mass of CaCO3. But that's fine because we can do that from the molar mass of CaCO3, right? The trick here is to get the number of moles. So in these problems, they're going to give you data related to pressure, volume, temperature. You use the ideal gas law to find out the number of moles. Or if they give you the mass of the reactant, which is a solid in this case, find out how many moles, and then again, 1 mole of this for every 1 mole of that, that will give you the moles of CO2. So again, you can find out any of them. So let me save this, and then 1.797 is what we have. So be careful with this one because in this particular equation, all the coefficients are 1. Okay, so this is how much reacted. If the coefficients aren't 1, then you got to take those numbers into account, right? Okay, so last step. Well, we want CaCO3. So what's the molar mass of CaCO3? Calcium is 40.08. Carbon is 12.01. Oxygen is 16. Okay, so I'm not sure offhand what that comes out to. I think it's like 108 or something like that. Let's see. 40.08 plus 12. Well, actually, well, I should be able to do this in my head. Let's try it. This would be 52.09, and this would be 48.00. So let's just do it that way. Sometimes it's harder to use a calculator. 100.09. Okay. All right. So again, if you have the number of moles and you want to find the mass, you multiply by the molar mass. So 1.797 moles of calcium carbonate times 100.09 grams per mole. And that's calcium carbonate. So boy, it's 179.7 grams, right? So 1.797 times 100.09, and you get 179.86 grams of calcium carbonate, but they wanted it to 3 sig figs, so 180 grams of CaCO3. Put the little decimal point there to get your third sig fig. Okay, so there you go. So be careful with that one, because if they give you a problem where the coefficients are not 1, you have to take that into account. But we did take it into account. It's just that it didn't change the number. Okay. Looking at this one, I'm just looking through a couple of other examples. Yeah, so there's some other examples where they give you, where they're not going to be 1, where the coefficients are not 1. So you can take a look at that. There's one in here that's kind of challenging. So I think what I'll do is tomorrow, which is Thursday, I'll go through, well, there's one more of these calculating the gaseous reactant that is a pretty challenging balanced equation. So I'll look at that one. We'll start that one off tomorrow. And then after we finish that up, we'll do gas mixtures, and gas mixtures are pretty simple. We'll do that. And then we'll get into the kinetic molecular theory of gases, and that'll wrap up the chapter. I suspect we'll wrap that up. Let me see how many problems did I put in there. Yeah, I put a few problems in there. So probably next Tuesday, we'll finish up chapter 10 and then start getting into the second half of the material, which is the stuff I find very interesting, which is quantum mechanics and quantum chemistry. So we'll get into that starting next week. Okay. So have a great day. Have a great week. I'll be back tomorrow with finishing up chapter 10 or getting close to finishing up chapter 10. And take care, everybody.
Thank you,
Have a good
Professor.
day. Thank you.